Hello, this is Shan Huang from National University of Defense Technology, the Hainan Lab. Today, I'd like to present our paper, DC4, Reconstructing Data Credit Coupled Congestion Control for Data Centers. Today's data center traffic exhibits complicated and time-varying patterns, from long-running flows to short-lived burst flows, which makes it a great challenge to prevent network congestion. As we can see, Server 1 and Server 2 are sending packets to Server 3. At the moment, congestion is forming at switch 5. In the beginning, packets are queuing in the congested queue. With time flows, continuous congestion causes packet dropping. Packet queuing and dropping are all harmful and can cause a sharp downgrade in network performance. Many congestion control schemes have been proposed to manage congestion. To understand congestion control more comprehensively and clearly, we make the first attempt to present a novel congestion control framework. That is, the data credit plan architecture. In addition, we summarize the full control loop procedures from 1 to 6 in the data credit plan architecture to analyze the workflow of the congestion control. At first, I will introduce the reactive congestion control and abstract their working processes in the data plan. DC-TCP, DC-QCN, and HPCC are working in the same way. They manage congestion based on the in-network feedback. The switch data processors attach congestion information to the data packets and deliver them to the receiver. After this, the receiver sends notification packets to the sender, and these packets carry the congestion information provided by the switch data processors. Timely and Swift manage congestion by the RTT information. The switch data processors are bypassed by them. Although the RTT information can reflect whole path congestion status, these schemes are unable to obtain concrete data queue length at each hop. In general, these reactive schemes have a long reaction period that takes at least 1 RTT. Besides, their feedback signals are flow-level coarse granularity, like ECN, RTT, and even INT. To manage congestion more accurately and fast, many receiver-driven congestion control schemes are proposed recently. Receiver-driven schemes may employ various control packets to drive data, such as token, pool, and grant packets. Since they all have the same functions as credit packets, we revert to all such control packets as credit. I will introduce and analyze their working procedures in the data credit plan architecture. NDP and HOMA work in the same way. The sender sends a data packet when receiving a credit packet, and the receiver sends a credit packet when receiving a data packet in return. However, they bypass in-network data processors and credit processors. Hence, they are invisible to data queue length, which will lead to in-network congestion. Polo improves the congestion control ability of HOMA and NDP. It uses switch data processors to feedback the in-network congestion. However, it neglects to use in-network credit processors to more accurately manage congestion. ExpressPass works in a different way than the others. Data transmission is totally controlled by the credit. In order to ensure the data arriving rate is within the link capacity, receiver and switch credit processors limit the credit sending rate accordingly. When the sender receives a credit, it sends a data packet accordingly. Meanwhile, the in-network credit congestion will be fed back to the receiver and the credit sending rate will be adjusted to mitigate congestion. In this way, the data can be accurately controlled by the credit plan. But since the data congestion is totally invisible, ExpressPass cannot prevent data congestion, especially under the considerable traffic outside of credit control. Here, we make a table of these schemes and find them are all within the scope of data credit plan architecture. However, they lack some control procedures more or less, making them inefficient in some aspects. Given that, we try to put forward a data credit coupled congestion control that uses all processors and performs all control procedures. However, this is not easy to achieve due to the existing challenges. The first challenge is credit loss. Assuming each switch allows only one credit to pass through within a given time duration, credit 1 passes through switch 3 and switch 2 successfully, but credit 3 and credit 2 are dropped. Then, credit 1 is dropped at switch 1 when credit 0 is allowed to pass. In this case, the links between switches 2 and 3 and between switches 1 and 2 are underutilized because no corresponding credit successfully arrives at the sender. Credits 1, 2, and 3 are all dropped. The second challenge is duplicated feedback from both credit and data plans. At the beginning of the flow transmission, the receiver sends credits to the sender at the rate of 8 packets per second, we name it PPS. However, the credits are congested at the credit processor of switch 1, and then the rate is cut to 4 PPS. As the credit drives data in a one-to-one manner, the sender sends data packets at the rate of 4 PPS. When the data flow arrives at the switch 2, the data processor of switch 2 is congested and the flow transmission rate is dropped to 2 PPS. Consequently, the congestion feedback will be duplicated delivered from both the credit and data plans. And this may lead to excessive congestion reaction. To solve these two challenges, we proposed ECN-based credit rate control, queuing the credits and adjusting the credit sending rate when the queue exceeds a threshold to prevent credit loss. Besides, we employ ECN as the congestion signal from both credit and data plans to avoid duplicated congestion reactions. Inspired by the data credit plan architecture and the challenges, we developed DC4, mainly composed of 3 parts: ECN-based credit rate control, speculative probe, and retransmission strategies. This is the framework of ECN-based credit control in DC4, including switches, senders, and receivers. Receivers send credits via credit paths to pull data packets from senders. Switches mark credits and data packets with ECN labels when the credit queues and data queues are congested. As we can see, receivers are sending credits to senders. In the switches, the credits are rate limited in the credit queue to prevent data congestion on the reverse path. The credit processor of switch 1 marks the ECN label on the credits when the queue exceeds the threshold K credit. Then, the credits are delivered to the senders. At the sender, data packets are scheduled one by the credits. When the sender receives a credit, it first records its ECN label and credit sequence number in the corresponding scheduled data packet. In addition, the sender assigns an incremental data sequence number to the corresponding packet. The credit and data sequence numbers are used for retransmission. When the data queue length exceeds the threshold K data, the data processor marks the data packets with an ECN label. Otherwise, the switch discards data packets when the data queue overflows, and the sender performs data retransmission based on the data sequence number. When the data packets arrive at the receiver will update the credit sending rate based on the Shan algorithm By doing this, data queue congestion and credit queue congestion both can be regulated by the ECN-based credit rate control mechanism. However, the ECN-based rate control is not enough to achieve high-speed transmission. Due to the credit request process, data cannot be transmitted in the first RTT, and the bandwidth is wasted. Therefore, we try to directly send probe data packets at the beginning instead of a credit request. And a probe packet is another kind of data packet. It carries the information that is necessary for the receiver to generate and send credits. However, since the probe packets are out of the control, they may be congested and lead to packet drop. When a packet is dropped in the last part of the flow, corresponding to an amount of data equal to the DTP, the impact on the FCT can be more serious. Therefore, to mitigate the impact of data loss on the FCT, we are motivated to drop normal packets rather than the last DTP packets in the case of buffer overflow. Similar to the definition of the BDP, we define the DTP as the data transmission rate multiplied by the base RTT. Then we need retransmission strategies to ensure data integrity. Each credit carries two kinds of sequence number, including data and credit. The host can easily determine the number of data or credit packets lost by calculating the sequence difference between two continuously arriving packets. It is unnecessary to retransmit the origin lost credit because the data packet related to the lost credit can be driven by any other credit belonging to this flow. Besides, it is unnecessary to resend the credit immediately, as uncontrolled credit would disturb the credit rate control mechanism. To evaluate the performance of DC4, we develop a simulation environment based on the OMNet with the INET framework. We use a leaf span topology with 24 leaf switches and 8 span switches connected to 480 host nodes. The network base RTT is set to 16 microseconds. The figure shows the average per flow data loss and credit waste of DC4 and ILS under different loads with various realistic workloads. ILS suffers from severe credit waste under every kind of workload, with a large number of credits being dropped due to overspeed, which will result in data throughput degradation. In contrast, DC4 benefits from ECN-based credit rate control, and the credits are rarely dropped at any node in the network. Besides, the data loss is more severe in ILS than in DC4, mainly because the data credit coupled control design in DC4 helps both credit and data react faster to bursty traffic and data queuing in the network. This figure shows the FCT slowdown for the 30% shortest flows, the average FCT, and the 99th percentile tail flows FCT under loads of 0.4, 0.6, and 0.8 with 4 realistic workloads. As we can see, DC4 performs better than all the compared schemes. This figure shows the average good-put of DC4, HPCC, ExpressPass, and ILS under different traffic with various target loads. The ECN-based credit rate control and speculative probe allow DC4 to mitigate credit waste and the first RTT bandwidth waste, making its average good-put the closest to the ideal. This figure shows the average and average maximum queue length of each switchboard, with different loads under continuous background traffic. We evaluate data queue length with and without the data queue ECN marking mechanism, that is DC4 and DC4 alpha. Thanks to the data queue ECN marking mechanism, DC4 outperforms DC4 alpha in terms of both credit and data queue length. This figure shows the good put of the receiver and the good variance of senders in the scenarios with different degrees of incast. The average good put variance of the senders is small because of the fair convergence of the ECN-based credit rate control algorithm, and the average good put of the receiver remains almost the same because data transmission is precisely controlled by the credits. To conclude the paper, we first present the data credit plan architecture, and then we develop DC4, the data credit coupled congestion control. The simulation results show that DC4 performs better than the state-of-the-art congestion control schemes. That's all. Thanks for your listening.